In section 1.2, we look at the statistical and critical thinking concepts. The key concept here is to further analyze our descriptive statistics. This section provides an overview of the process involved in conducting a statistical study. The first thing we need to do is prepare our data, and by prepare, I mean we need to understand the context in which the data is collected. What do the data mean? What is the goal of the study? What is the source of the data? And what sampling method was used? These things would influence maybe how you saw the data. For example, if you knew that Hershey Candy Company science researchers were trying to find a link between increased chocolate consumption and lower cholesterol, you might be suspect of any research they perform or put forth that supports the claim that consumption of chocolate lowers cholesterol. However, if you looked at an independent researcher who came up with the same conclusion, you would not be quite as skeptical. Just simply because of the context of the study, you perceive that some sort of a bias has been introduced. And after you prepare your data, understand the context, know where it's coming from, understand how it's collected, then you're ready to analyze the data. That is, you want to perform some statistical tests to get to see what the description is, the population distribution, what does it look like, and then you'll form a conclusion. When you're preparing the data, you want to make sure that you've removed as much bias as possible. Does the method chosen greatly influence the validity of the conclusion? Are there voluntary responses or self-selected samples are used in the collection of the data? These do tend to increase bias. They increase bias because those with special interests are more likely to participate in them. Other methods are more likely to produce good results, especially if those methods involved randomization. Once you've collected your data, you've prepared it, you're now ready to analyze the data by graphing and exploring. Every analysis should begin with the appropriate graphs. In Chapter 2, we'll get a better idea of what some of those graphs will look like. Also, in analyzing, we need to apply statistical methods and determine whether or not these methods, based on the technology that we have, are they required to use good common sense, and are they paying attention to sound statistical methods? Sometimes the answer is yes, sometimes it's no. And if you run across a study that you think is not using sound statistical methods, then it's up to you to speak up. In conclusion, our conclusion could be that the data have a statistical significance. By that we mean that it is very unlikely to see the observed values occur by chance, meaning there is something going on. It's not just a fluke that we got this result. That if that happens, then we say that the data has statistical significance. However, just because statistical significance exists does not mean that practical significance is going to exist. You need to state the practical implications of the results, not just whether or not they're statistically significant. Common sense might suggest that the finding does not make enough of a difference to justify its use or to be practical. Here's an example scenario. In a test of Atkins weight loss program, 40 subjects had a mean weight loss of 4.6 pounds after 1 year. The 4.6 pounds is statistically significant. However, if you're trying to lose weight using a radical diet like Atkins, this 4.6 pounds is not a very practical expectation for weight loss. So there's a situation where statistical significance loses to practical consideration. There are some potential pitfalls or misleading conclusions that can cause issues whenever you're dealing with data and statistics. One thing that causes confusion is that concluding that one variable causes the other variable when in fact the variables are only correlated or associated together. Two variables that may seem linked are smoking and pulse rates. They may be linked, but does one variable cause the other? Does smoking cause a faster or a slower pulse rate? Or does having a faster or slower pulse rate cause you to be more inclined to smoke? I don't know. But these are things that you've got to look out for. A correlation does not necessarily imply causation. We cannot conclude that one causes the other, so correlation does not imply causality. Another potential pitfall is selecting or running data based on samples that are too small. Conclusions should not be based on samples that are far too small. For example, basing a school suspension rate on a sample of only 3 students would not be wise. What if you happen to select 3 very well-behaved students who are never expelled? Can you conclude then that that entire school has no expulsions? No, because your sample wasn't large enough, nor was it random enough. Let's say you're walking down the hall where all of the detentions are, where all the troublemakers are, and you survey those students, and 2 out of 3 say, yeah, I've been suspended. Are you comfortable then saying that 66.67% of the students in that school have been suspended at least one time? No, your sample is too small. You need to survey more people in order to get a better idea of what's really going on with the school. Another potential pitfall is something that we call loaded questions. The loading of the questions could either be intentional or completely unintentional, but it still happens. Here's an example. If survey questions are not worded carefully, the results of a study can be misleading. When pollsters asked respondents, should the president have the line item veto to eliminate waste, 97% of them replied yes. The president should have the line item veto to do good things, and in this situation, the good thing that he wants to do is eliminate waste. But when we take off that reason from the question and just ask a plain Jane question, should the president have the line item veto or not, only 57% of people surveyed said yes. It's a big difference because you stuck on this emotionally charged issue at the end of the statement. Another potential pitfall is the order of questions. Questions are unintentionally loaded by such factors as the order of the items being considered. When asked this question, would you say traffic contributes more or less to air pollution than industry? Traffic was worded first, it got the highest response. Now, when we reversed the order between traffic and industry, and we were asked, would you say industry contributes more or less to air pollution than traffic? Well, then industry took the big hit. Whatever was listed first, that's what got the largest hit. I'm not offering a reason as to why, it just is an observation that happens. Another potential pitfall when gathering data is the non-response. Now, a non-response just means somebody refused to answer the survey. That doesn't mean that their response was not valid or that it was lost. They just refused to answer. And the fact that the non-responses are on the rise amongst surveyors does speak something about our society as a whole. Some people hypothesize that non-responses are increasing because as society we are losing more and more of our privacy to internet spying and a desire to remain off the grid. Don't want to answer questions. But non-responses occur when someone either refuses to respond to a survey question or they're unavailable to respond to the survey question. We treat them the same. They're people who refuse to talk to pollsters. They do have a view of the world around them that is markedly different from those who will let pollsters into their homes. Another potential pitfall is missing data. Missing data can dramatically affect the results. Subjects may drop out for reasons unrelated to the study, in which case you'd have a confounding effect. For example, people with low incomes are less likely to report their incomes. The U.S. Census suffers from missing people that tend to be either low income or homeless. Another potential pitfall with statistics are precise numbers. Because a figure is precise, many people incorrectly assume that it is also accurate. For example, I could say 98.645 statistics are made up on the spot. Because that's a very precise number, I'm going to have more people believe what I said was true because I used a really precise number. when in reality, only 23% of all statistics are made up on the spot. That's a lie as well. I just made that one up too. A precise number can be an estimate, and it should be referred to as that way. You should say about this many people make up statistics on the spot. We're getting close to the end here for potential pitfalls, and that is percentages. Percentages can be misleading or unclear percentages that are used. For example, Continental Airlines ran an ad exclaiming, "We've already improved 100% in the last 6 months with respect to lost baggage." Well, if they've improved 100%, then that means that they've lost no bags. I'm not sure that's what they really meant, because I'm sure they're still having lost baggage. But in this situation, 100% is misleading. We don't know what it means. Did they lose 100% more of the bags than what they had? 100% less? If they lost 100% less, then that means they lost no bags. Did they make no mistakes? That's doubtful. So this wraps up section 1.2.